Our speaker tonight is Dykaar. She is a PhD right there. She is a PhD student at the Dunlap Institute and Department of Astronomy and Astrophysics at the University of Toronto. Her research focuses on sources known as tidal disruption events, which are stars that are being ripped apart into black holes in the center of galaxies. She previously received her bachelor's degree from McGill University in Montreal, and in her free time, she enjoys swimming, walking, and drawing. So now, tell us about tidal disruption events.
Yeah, thank you, Simran, and thanks everyone for coming. Can everyone in the back hear me okay? Okay, awesome. Yeah, so my name is Dykaar. I'm a graduate student here at the University of Toronto in the Department of Astronomy, like Simran was saying. And I'm also associated with the Dunlap Institute. And so tonight I'm going to be talking to you about what I'm studying for my thesis, which are called tidal disruption events. And the subtitle of this talk is When a Black Hole Destroys a Star, which is a kind of brief explanation of what a tidal disruption event is. But I'm going to start the talk by giving you a more technical definition. So the technical definition of tidal disruption event is when the tidal forces between a supermassive black hole and a star exceed the star's self-gravity. So this definition has a lot of jargon and words that aren't used in like everyday conversation. So we're going to start by breaking down some specific terms. Okay. So we'll start by talking about what are tidal forces, what are they caused by, and what are the consequences of them. We'll then get into what is a black hole. A lot of people have heard the term black hole, but really breaking down what does that mean, and then specifically what is a supermassive black hole. And then what is self-gravity? How does that play a role? And then we'll put it all together to figure out how all of these things paint a picture of a star being destroyed by a supermassive black hole. And throughout this talk, I may refer to tidal disruption events by their acronym TDE. Okay, so starting off, like I said, with tidal forces. So many people here are probably familiar with one of the most present in everyday life consequences of tidal forces, and that's the tides of Earth's ocean. So if you don't know what tides are, basically, if you stood in the same place, twice a day, the level of the ocean would rise, and twice a day it would be lower. And the reason for this is actually because of tidal forces from the moon. So how could the moon be affecting Earth's oceans? We'll start with a very simplified diagram. This is not to scale. So we have Earth, and we have it surrounded by a layer of ocean. Nearby, we have our moon. The moon has mass, and anything that has mass exerts a force of gravity on everything that has mass around it. And this force of gravity is an attractive force. So you might think that that means that the moon will simply attract Earth. But it's a little more complicated than that, because not only does mass matter, but also distance matters. So the closer something is, the stronger the force of gravity it feels. Which means that the near side of Earth will feel a stronger force of gravity from the moon. So it's going to get pulled the most. Again, not to scale. The center of the Earth is going to get pulled the medium amount, we can call it. So it will be pulled towards the moon, but not as much as the near side. And then lastly, the far side will get pulled a little bit. And this is what a consequence of tidal forces. So the tidal forces is called differential gravity. So the force of gravity is different depending on the distance to the object. And so the consequence of this is that Earth gets tidally squished. And so no, it is not this exaggerated, but it is actually what's happening. And we know it's happening. You can see the consequence yourself. If you were to stand on Earth and wait for it to go around once every 24 hours, if you stood on the surface of Earth and waited, you would experience low, high again. This is because of tidal forces from the moon. The moon is not the only object that exerts tidal forces. The Earth exerts tidal forces back on the moon, and this happens throughout planets and moons in our solar system and other solar systems. But the tidal forces of the object I want to talk about are tidal forces from black holes. So like I said, many people have probably heard of black holes, but may not really understand what constitutes a black hole. And in order to understand that, we have to talk about the concept of escape velocity. Escape velocity is the speed you have to be going in order to escape something's gravitational pull. So we will go back to Earth again for our example. Let's say that you want to escape Earth on a rocket. You have to exceed a certain speed. So you know this because if I were to toss my phone into the air, which I won't do, it will fall back down to Earth. And that's because Earth's gravity pulls it back down. But if I were really strong and I threw my phone as fast as a rocket, then you could picture that it would escape Earth's gravity and fly off into space. And that's because it is exceeded this escape velocity. So how do we know what the escape velocity is? Well, it depends on two things. The first is mass. So if the more massive something is, the faster you have to be going in order to escape it. So if you were to make Earth more massive, it would have a higher escape speed, it would be harder to get out. The second is radius, or distance. So if you were to try to escape from, say, Earth's orbit, you wouldn't have to be moving as fast. But if you try to escape from the surface, you have to be going faster. And similarly, if you're able to make Earth smaller, a smaller radius, compact the mass more, such that you were closer to all of it and standing on the surface, that would also increase the escape speed. So you'd have to be going faster. So these are the two components that decide what something's escape speed is. And you can imagine a scenario where either you increase the mass, or you decrease the radius, or you do both, that you make the escape speed go faster and faster and faster and faster, so it's harder and harder and harder to escape. And you could get it all the way up to, oh, there you go, the speed of light. This is the speed limit of the universe. Nothing moves faster than light. It's approximately 300 million meters per second. So if you have an object where at some distance you have to be going faster than the speed of light to escape it, that is what a black hole is. Now, black holes range in mass. The lowest ones are around a few times the mass of our sun, which is already mind-blowing, because our entire planet, everything that we exist on, is a tiny fraction of the mass of our sun. The smallest black holes, 3 times the mass of our sun. But they go all the way up to millions or billions of times the mass of our sun. And these have a special, very creative name, supermassive black holes. And these are the black holes that exist in the centers of galaxies, like this one. This is the Andromeda galaxy, which is the closest galaxy to our own. And the bright spot in the middle, inside that, is where the supermassive black hole is. Now you may be thinking, how do you know that? You just said even light cannot escape it, so we can't really look at the black hole itself. One of the key ways that we know that the supermassive black hole is in there, and in the centers of most, if not all, galaxies, is because we can see how it gravitationally interacts with the stuff around it. So I'm going to play you a video now. Hopefully, we'll see. So this is work done by Andrea Ghez and her group at UCLA using data from the Keck telescope. And this is a video of the orbits of stars in the center of our own galaxy. And because they knew the mass of the stars, and they can track the speeds of the orbits, they can back out what the mass and the size of what they're orbiting has to be. And they can figure out what the escape velocity is, the dynamics of the object, and figure out that it has to be a supermassive black hole. And this is work that won Andrea Ghez the Nobel Prize a few years back. And if you're wondering about the timing of this, 2 years in real life is a second in the video, so it's about 20 years of data that we're watching. Okay, that's the end. Another way that we know is we can just take a picture, but that's a very recent development. So these are 2 images of the supermassive black hole in our own galaxy, Sagittarius A star on the right, and of M87, which is the Andromeda closest galaxy to us on the left. So this is a very recent kind of mind-boggling development that we're able to image the black hole, which is the dark center part of these images. And I'll get into a little bit how you can actually do that later in the talk. So we know that black holes exist in the centers of galaxies. I want to show another kind of recent astronomical image that maybe you are familiar with. This is the James Webb Space Telescope Deep Field image. And what you're looking at here is kind of just like a point in the sky that the telescope was directed at. And every single blob there, except for like the 4 or 5 that have spikies, those are stars, every single other blob is a galaxy. And so all of these galaxies permeate the universe, and inside the centers are supermassive black holes. So now we come to kind of the last piece of the puzzle of our definition, and that's self-gravity or self-gravitation. And this is what holds stars together. So if you have a star, chilling, existing, what holds it together is the force of gravity of itself. So the mass of the star pulls in on all of the other mass and keeps the star together. So if this star were to encounter some sort of tidal forces, similarly to how our Earth encounters tidal forces from the moon, it could also start to get squished in the same way as when I described why the Earth gets squished by the moon. If you squish it enough, eventually it will overcome the self-gravitation forces, and then it shall explode. So now we have all of the components, so we can discuss how supermassive black holes destroy stars and to create a tidal disruption event. So we start with a black hole. There's some distance around the black hole that we call the tidal radius. This is the distance that the tidal forces overcome the self-gravitation forces. As a star approaches the black hole, if it's on an orbit that's going to enter this tidal radius, first it starts to get distorted as it approaches. It then enters the tidal radius and explodes. Some of the material will remain bound to the black hole gravitationally. Some will remain unbound, which means it flies off into the universe. And I hope everyone enjoyed this little diagram that I made in Google Slides. But the cool thing about giving a talk in astronomy is that there's always pretty videos that you can find that show whatever you're talking about. So I'm going to play a video from the DESI Science Communication Lab. Hopefully, again. And this is an animation, an artist impression animation of what happens during a tidal disruption event. So this is the supermassive black hole with some dust and gas orbiting around it. Uh-oh, here comes the star. So as it approaches, it starts to get tidally squished. And as it enters the tidal radius, it's destroyed. Some of the material flies off. Some stays gravitationally bound and starts swirling around the black hole. And there's some other kind of perpendicular outflows associated as well, which we'll talk about. OK, that's good. Where's my cursor? OK. So how do we observe these things? So the way that we observe these depends on the basically exactly what you just watched in the video. So the first important component is the material that was swirling around the black hole. So like I said, around half of the material remains bound gravitationally to the black hole. So a common misconception about black holes is that they act like vacuum cleaners and they just instantly suck everything in. But actually what they're doing is they're just interacting with the stuff around it gravitationally. So for example, if we were to somehow replace the sun in our solar system with a black hole of the same mass, we wouldn't even notice. Well, we would notice because we would die. But the orbits of the planets, wouldn't notice. They would remain the same. So similarly to how sun's gravity makes Earth orbit it, the black hole's gravity makes all the stuff around it orbit it. So when the star is destroyed and the material gets gravitationally bound, it starts to swirl around the black hole. So we're going to zoom in a little bit on this section. OK, so if we could zoom in really fast, really far, and see what was happening, it's a lot of particles moving really, really fast, high speeds. Some of them are going to collide. And when these fast-moving particles collide, they cause friction. And friction heats them up. And hot stuff glows. If anyone has ever seen metal or glass being heated up, it starts to glow. And different energies of hot things will glow in a different way. And the reason for that is because light is a wave. And depending on the wavelength, so the crest to crest distance, the light will be a different color. So if you've ever seen a gas stove or a picture of a gas stove, if you turn the heat all the way to its highest amount, the flame turns blue. And this is because blue has a shorter wavelength and a higher energy. So our eyes are actually able to see what the energy of light is. However, there's a catch. Our eyes are only actually able to see a small section of what we call the electromagnetic spectrum. So that middle part that we call visible is everything that our eyes can see. But there are all of these other parts of the electromagnetic spectrum. And as astronomers, we like to look at light from each of these sections in order to build a complete puzzle of what is going on. So the other sections, if you were able to see, which we can't with our eyes, but we can with telescopes, something even redder than red, infrared. This is, for example, what a dog would look like. We have the microwave section, which we use to heat up food. The radio section, this is the longest wavelength and shortest energy section. If we go more energetic or shorter wavelength than what we can see, we have ultraviolet light, X-rays, which we can use to look at our own bones, and gamma rays, which I was told last night is how the Hulk got made. I don't know. But going back to TDEs, the reason I'm telling you all this is that that friction that heats up the accretion disk from a tidal disruption event will make that disk, I don't know if I mentioned this, the accretion disk is what we call the stuff swirling around the black hole. The accretion disk is going to glow brightest in ultraviolet and X-ray light. And that is how we first discovered TDEs. So the first candidate tidal disruption events were found in an X-ray survey. And survey in astronomy just means a picture of the sky. So sometimes you take a telescope and you're like, I want to look at that specific thing, and then you do it. But sometimes you take a survey, which means you just take an image and then see what you find. Well, you have to write a proposal, so you should know what you're going to find, but anyways. So we found 4 from that. And as time went on, we also found signs of this accretion disk in ultraviolet light and optical light as well. And optical is what astronomers call the visible light that you can actually see. But I study radio light. So I study the longest wavelength and lowest energy light coming from tidal disruption events. Now you might be thinking, why would you do that when you could study the X-ray or the ultraviolet where the accretion disk glows? Well, there are other outflows associated with the star being destroyed that actually are brightest in radio. So going back to our picture from before, you may have noticed that there's these perpendicular beams of light. So these arise because of the magnetic field of the black hole and charged particles in the disk. And they shoot the charged particles at close to the speed of light, perpendicular from the disk, and we call these jets. And these jets glow brightest at radio. There's also a wind that comes off of the accretion disk, so not material flowing all the way into the black hole, but kind of a wind that also glows brightest in radio. And then lastly, the unbound debris flying off of the system may also be producing radio light. So I mentioned that the first X-ray TDEs were discovered in the 90s. The first radio observation of a TDE was pretty recent. It was 2011, and it was called Swift 1644. So Swift is the name of the X-ray telescope that discovered it, and 1644 just has to do with its position. So it was discovered similarly to the rest of them in X-ray light, but this source was interesting because when we looked at it with radio telescopes, we actually saw this bright radio jet. So this opened up a new way to observe tidal disruption events, which was by looking at their radio light. So a few years after that, in 2016, another radio tidal disruption event was found. This one is called Assassin 14Li. It has a really fun name. Assassin is the name of the X-ray survey that discovered it, and then 14Li again has to do with its position. So it too was discovered in the X-ray section of the spectrum. But when it was looked at through radio telescopes, we didn't see something that looked like a radio jet, but we did see some radio light. And actually, it's still debated why. So the two main guesses are the ones that I mentioned before, either a wind coming off of this disk or the unbound debris flying off into space. So there are about a handful currently of tidal disruption events with radio observations. So the first is, why do only some TDEs launch these radio jets? So when we found the jet coming off of 1644, we were like, whoa, that's cool. Let's look at all the other ones and look at their jets. But then we looked at all the other ones with radio telescopes, and they didn't have radio jets. So we were like, whoa, that's weird. The other is, what is causing this faint radio emission? So like I mentioned, we don't know exactly why Assassin 14Li is even bright in radio. So that's an ongoing question. And then, are all of them bright, like Assassin 14Li? So this is the puzzle piece that I am working on, which takes us to radio observations. So when I look at a tidal disruption event through a radio telescope, I don't look at what I showed in the video. You can't watch live as a star is ripped apart. You cannot see all of the details like that. And that is because, like I said, we are looking at supermassive black holes destroying stars in other galaxies. So we're looking really far away. So when you observe another galaxy or something happening in another galaxy, what you see is a dot, if you're lucky. But actually, more accurately than a dot, you see a blurry dot. And that is because when light enters an aperture, it gets spread out. We call this diffraction. And two things change how blurry that is going to be. The one is the size of the opening. So if you've ever bought a telescope, you may have seen the size of the aperture advertised. And that's because the bigger the aperture, the more light you collect, the less blurry or less spread out the light will be. But unfortunately for radio astronomers, the other component is that the longer the wavelength, the blurrier your image will be. And if you remember, radio is at the far end. It's the longest wavelength, it's the lowest energy. So if you wanted the same sharpness for a radio image as for an optical image, you would need a telescope 1,000 times bigger. And so they do that. This is the FAST telescope. This is 500 meters long. But obviously there is a limit, construction-wise, of how big you can make a telescope before it collapses. This is the biggest one. So there's another creative thing that radio astronomers and engineers came up with, which is called interferometry. So interferometry, we're not going to get too deep into it, but the basic idea is that you have several smaller radio telescopes that you can then combine the images to make it like a big telescope. And this is how we got these images that I mentioned earlier of the supermassive black holes. This is from telescopes all the way around the Earth that combined their images to make a telescope the size of Earth. It's also the technique that's used in the telescope with the data that I use. This is called the Australian Square Kilometer Array Pathfinder. So this is 36 dishes, you can see here. I went for the aesthetic picture, which is actually a little bit hard to see. It's like nighttime, but you can see some of the dishes. 36 of them, 12 meters each in diameter. And this telescope is the fastest radio telescope on the planet. I forget the number, but it reads more data every day than all of the Australian internet. And I don't know how that compares to the Canadian internet, but it's a lot of data every day. And using this telescope, they are conducting several surveys, which I mentioned is like a giant picture of the sky. And one of these surveys is called VAST, Variables and Slow Transients. And I'll get into what those words mean. But basically, it's a repeated image of the sky, is what the survey is. And the reason that they want a repeated image of the sky is because a variable source is a source that changes in brightness over time, which is what a tidal disruption event would do. The way that an astronomer depicts this, a change in brightness over time, is with a plot called a light curve. So a light curve is brightness over time. So getting back into observing tidal disruption events with these radio telescopes, what will we actually see when we're looking at it? Well, when the star and the black hole are far apart and not interacting, there won't be any light produced. So the brightness, which is the y-axis, will be low. So the first time point, we're going to have low brightness because nothing's happening. We wait a little bit longer, still nothing's happening. But then the star starts to get disrupted, light starts being produced by the mechanisms I mentioned earlier, and the brightness starts to go up. And the accretion disk is forming, and and the jets are being produced, the brightness is going to peak. And then when the star is done being disrupted, the brightness is going to go back down. So this is what we call a light curve, brightness over time. And this is what we call a transient or variable event, because the brightness is varying over time. So what would that look like? Well, it would look like a dot. It gets brighter, and then it gets dimmer, again, if you're lucky. Okay, so how do we know what we want these light curves to look like? What are we searching for in these light curves? The way we know what we want to look for is we make a simulation. So we make a model TDE, and we say, okay, it's going to happen at this point in the sky, at this time, with this energy, this orientation, and make a lot of them based on how often we think they're going to happen. And then we say, okay, this is what the model tidal disruption event light curve is going to look like. And then we say, okay, what if we took the pictures of our simulated sky at the same time that we're going to take the pictures with our survey of the real sky? Now what will they look like? Well, we might have missed some. We might have missed a big chunk. Beginning, the end. Maybe it was so far away that we can only see the brightest points. But now at least we know what we're looking for. And then we get to the data. So this is what the data looks like. So my brother, when I practiced with him, he's like, wow, you spend all day looking at dots, and this is true. So this would be observation 1. And we can plot the brightness. Oh, well, I should mention, you might be looking at that and say, I don't even see a dot in the center of that picture. That's fair. But there's a second step where we run it through a computer algorithm that tells us whether the probability that there's a dot there. So what the algorithm does is looks for islands of pixels that are some level above the noise. And so the algorithm was like, no, trust me, there's a dot there. And so once we know there's a dot there, we say, okay, well, what's the brightness of the dot? Let's make a light curve. We plot the dot on the light curve, and then we say, okay, let's go to the next observation. And that's the brightness of the dot. And we just keep going. Sometimes the brightness won't do anything interesting. It won't look like a tidal disruption event, so we'll chuck it in the garbage. But sometimes, lo and behold, we'll get something that looks like this. And that, it kind of looks like the model. And so we say, this looks pretty convincing. This might be a tidal disruption event. It agrees with, the energetics and the time scale of our model. But is there another clue that we can use that will tell us, that will convince us more that this is a tidal disruption event? Well, if you remember, I said that tidal disruption events are stars being ripped apart by supermassive black holes. And supermassive black holes are in the centers of galaxies. So we want to look for the sources that have light curves that match our models that are coming from the centers of galaxies. And the way we tell this, we go back to our electromagnetic spectrum and we use visible light, because galaxies are bright at visible light. So I'm going to play another video. This is an animation of data from an optical survey called the Sloan Digital Sky Survey. And this is an animation of the position and type of galaxies of 400,000 galaxies. So I just think this is really pretty, but it's showing, using optical surveys, we can tell where in the universe these galaxies are. It's kind of like hypnotizing. Okay, that's good. So this is what the actual data looks like in a different color scheme. But this green circle shows the location on the sky of the radio source that I had previously shown. And you can see it's coincident with something that our optical survey is saying is a galaxy. You can zoom in further and see that the coordinate is coming from the center. And so we can put these together and show that there is a radial light curve that looks like our model tidal disruption event coming from the center of our galaxy. And this doesn't look that pretty, but I want to remind you what we are likely looking at is a star being pulled apart via tidal forces from a supermassive black hole at a galaxy somewhere far away in our universe. So yeah, I'd just like to take this time to thank the organizers of the talk, especially Simran and Isha, for organizing all of these events every month. And I really want to thank all of you for coming.
Thank you for that really amazing talk, Hannah. It was very interesting. Before we take some questions, we'd first like to invite everybody to, talk to your neighbors for a minute, talk about, any questions you might have, what you found really interesting, and then we'll take some questions. When we get the questions, well, obviously you'll get to choose the people, but
repeat the question. Yeah.
I forgot to tell you.
Thanks.
If you want, you can say the questions.
Okay. Did I? Oh, I think my phone is under here, sorry. I don't know, I didn't, my talk was really short, so you can look at me.
Okay, I think we can probably start taking questions now. So yeah, so raise your hand if you have a question. You can choose the people.
I choose?
Yeah.
You. Yeah.
Okay, I have two small questions.
Okay.
First, what's the difficulty of radiation of the tidal destruction event? And the second is, I guess I can reconcile, like, for the perpendicular, that ray, like, you said for one it's light speed, near light speed, so I feel like it's high energy, but at the same time it's radio, so then it's low energy. So I don't understand, it's like, is it actually high energy or low energy?
That's a really good question. Okay, I should repeat them. So the first one is, what is the duration of the tidal disruption event? And the second one is, if the jet is moving at high energies, why is the light that it emits low energy? So the first one, the actual time scale of the event itself is going to be around days. The light that you can get out of it depends on which frequency you're looking at. So one of the advantages, actually, of looking at a tidal disruption event in radio is that, like you said, radio is low energy, so the light that produces from radio waves is going to last a lot longer. But anyways, it's days for shorter wavelengths and like months for longer wavelengths. It also depends on the type of star that's disrupted, but those are the general scales. Why jets produce radio waves specifically has to do with the emission mechanism. So because it's coming from charged particles in magnetic fields, it's producing synchrotron emission. I need to explain this. Yeah, it has to do with the emission mechanism. So it's actually not thermal energy. So thermal energy scales differently with energy to tell you what the peak actually is. That's how you can tell, like, if it's hotter, it's bluer, if it's colder, it's redder. But you also have to take into account what the type of the emission is. And the type of emission coming from jets is synchrotron, which is the wavelength that it produces is radio. I'm not sure if that properly answers your question, but yes, it has to do with the way that the light is being produced is different for an accretion disk than it is for a jet. Yeah, no problem. Other questions? Yeah. If the stars collided before they were disrupted? If they collided while they were being disrupted, it would impact because it would be more material that's getting disrupted at once. So yes, you'd have brighter emission. Yeah. Yes.
You said the duration stays.
Yeah. Yes. Oh, so the question was, these are short-lived events, so you kind of have to get lucky to find one. And the answer is yes. Yes. That is a good question. So the rates are actually kind of unknown because we don't have a ton of observations. So when I calculated the rates that I was going to find, for example, in like a 2-year-long survey, I got 2 as a conservative estimate. So that kind of gives you a general idea. But yeah, the rates are a little bit unconstrained right now. Yeah.
Do you learn a lot about the mass or speed of the stars when you observe these events? Like, does the brightness tell you anything about that?
So the brightness tells you more about the system as a whole than the star specifically. The way that you can tell things about the star specifically is different masses of black holes will only be able to disrupt different types of stars. So when I was talking about the tidal radius, that it depends on when the tidal forces are able to overcome it. And you'll only be able to get a tidal disruption event if that distance is outside of the event horizon. So the event horizon is the distance where nothing can escape with black hole, not even light. And so if the tidal radius is inside the event horizon, then you won't see it. And so by knowing that a tidal disruption event happened, you can back out that the tidal radius must be bigger than the event horizon, and you can back out how strong the star needed to be, basically. So that's how you can tell something about the star. Oh, did I repeat the question? The question was, can you tell anything about the star from a tidal disruption event? But somebody, yes, in the back. That's such a good question. So the way we originally realized it was happening was before we ever observed it. So this professor named Professor Martin Rees, he theorized that this should be happening by saying, okay, we know there are stars in the centers of black holes. And this was before we even knew there were supermassive black holes in the centers of galaxies. We thought there were. And he said, okay, we think they're there. We know there are stars there. Surely a star is going to get close to one and get... So he theorized that this was happening before we ever saw it, back in like the 70s. So we knew to look for them based on the theory first, and then we found them. That's a really good question. Adam?
How bright is it?
Gosh, so it depends what frequency you're looking at, and then you need to figure out how far it is. So there's 2 types of ways of defining bright. So there's how bright something actually is, and then there's how bright it looks to us. The further something is away, the less bright it's going to look to us, right? So how bright it is basically the limit that our survey can see. So we can see them as long as they're bright enough of whatever survey you're going to see. In terms of how bright it actually is emitting, I don't have the numbers off the top of my head. You stumped me. I'll get back to you because we live together, so I'll let you know. Dad. Yeah, okay, the question was, is there any directionality to the radio source of the jet? Yes. So if the jet, so for example, when I was talking about Swift 1644, I said we saw a radio jet. We specifically saw a radio jet that was so bright it had to be pointed directly at us. So there could be sources that we're missing because the jet is just pointed away from us. As the jet goes through space, it also spreads out. So we can see jets that aren't pointed directly at us. They'll eventually spread to become spherical. So we should see all of them eventually, but they'll be less bright. Yes. Okay, so the question was, can multiple stars be destroyed at the same time? And then how will the magnetic forces affect the debris? So yeah, theoretically, multiple stars could be destroyed at the same time. I think it would be very difficult for us to tell in the data. We would probably just see a brighter emission. So it would be harder to say that it's because of 2 stars, unless they were separated by enough time. But if you're saying it's happening at the same time, we would probably view it all as one event. In terms of how the magnetic forces affect the emission, I'm going to have to be super honest and say I am not sure. Even the jets, I explained a very simplified version of how jets are formed. There's currently no complete model of how we know that jets are formed. We know it has something to do with the magnetic forces and charged particles, but the reason that it's kind of an open question of why do they not all launch jets is because we don't have a model that fully explains all jets. So how the magnetic forces interact here is pretty complicated. So it's a good question, but I unfortunately don't know the answer. Sorry about that. Yes.
Based off the spectrum, you're saying you're garnering information from the radio side?
Yeah.
And then you're trying to compare it with the optical side?
Yeah.
I mean, is there equipment or will there be equipment in the future that might measure the gamma side to get more clarity as you're talking about for that? Or is there no need to measure that? Are these models, are we getting much better at our models or something?
There definitely are gamma ray telescopes.
Yeah.
I think, yeah, so there sometimes is an associated gamma ray burst. So there is gamma rays associated at least with some of these tidal disruption events.
Okay.
Because I specified on the radio, again, I can't get too into detail, but yes, there is gamma ray information on these telescopes, and they're definitely, so SWIFT actually has a gamma ray detector as well. Yeah. Yes. Sorry, there's two kind of in front, but we'll do the back one first. Yeah. You. Yeah, I mean, so that's almost a little bit of a semantics question. So it kind of, if a star is spiraling towards a black hole and getting stretched and distorted, you could say tidal forces are destroying a star. Say tidal disruption event, specifically generally referring to a star as a massive black hole, and the star is completely destroyed because of how massive the supermassive black hole is. But you can talk about tidal forces or tidal disruption with other systems and smaller black holes as well. Yeah, so active galactic nuclei is kind of a very broad, encompassing term. So active galactic nuclei essentially means any galaxy, center of a galaxy, supermassive black hole, that is bright. So generally we refer to any supermassive black hole that is accreting as an active galactic nuclei. So it just needs to have material around it that's actively accreting. And then different systems can form around it. Like it could be jetted, it could be jetted at us, it could have a accretion disk, but yeah, basically anything that's accreting we refer to as an active galactic nuclei. Yeah.
So we probably have time for one final question.
Okay, yeah. That's a really good question. So, well, it depends. You can only get TDEs from certain sizes of black holes because of what I said. If the tidal radius is inside the event horizon, then you won't see it. But there's also different types of galaxies will have different amounts of movement of the stars. And so there's a theory that if the stars are moving around more, they're more likely to be disrupted. So a star or galaxy that has recently undergone a lot of star formations, stars moving around, or a galaxy that has recently undergone a merger, something that's going to whip the stars around more, will be more likely to have tidal disruption events, possibly. Yeah. Oh yeah, I think that's the end of questions.
Yeah.
Okay. Thank you for all of those questions.